I'm going to start off, I guess, a little bit talking more about Roland, and throughout, I guess, this presentation, I'm going to be spending a little bit of time kind of adopting his language and how he describes these projects, because this is built on 15 years of his research. So hopefully the language doesn't get too confused about any of that. But you could say that Roland's practices is kind of divided into two different branches. The one which is given over to practice, and then he also runs a research lab out of RMIT, which is essentially kind of like the breeding ground for a lot of the things that we then try to apply within real-world projects. So we do a lot of experiments and a lot of prototyping, and trying to kind of like adopt and perpetuate technologies and sort of different ideas of manufacturing. Okay, so I suppose one of the major things that Roland has kind of contributed towards this field is his explorations with multi-agent algorithms. And this is built largely on swarm behaviors, which is the idea of, I guess, an emergent style of behavior where behaviors are localized. So there's a localized intelligence within what we, within the practice, call agents. And this is built largely off the kind of discovery that a guy called Craig Reynolds came up with. These are his Void algorithms. And this was built on the idea, I guess, in the early days that when people were looking at, flocks of birds, they had the assumption that, there must be a larger kind of understanding of the overall swarm that's occurring there. Like either as a leader bird, or the birds somehow miraculously have a understanding of the overall form that they are generating there. And what Craig Reynolds came up with was that you don't need to have an overall understanding or a top-down approach to these elements in order to generate those swarms here. Basically, you need three basic behaviors, which is separation, the idea that no bird wants to get too close to another bird. Alignment, in that they try to generally align their behaviors towards each other. And cohesion, which is basically that they don't want to get too far away. And from this, you're able to generate a sort of flocking swarm logic. And you find this throughout nature fairly frequently in schools of fish or just basic emergent biological phenomena. So within the office, we don't try to sort of mimic biological phenomena. We basically just take this as a building block premise, and we start to generate our own behaviors within these ones. And we have about maybe a library of 3 dozen or so behaviors that we repeatedly come back to, and not every single project relies on all of those behaviors. We'll pick several of those ones, and they will be adaptive consistently throughout. So this is just an example kind of drawn out of a project that Roland did recently for the Centre Computational. They came up and they requested him to basically had a project that he did a while back, which was this sort of bridge proposal. They liked that. They asked whether he could do a little bit of a piece for it to go into their permanent collection. And what you guys can see here is basically every single one of these guys has a localized intelligence built into them, and the general form that's emerging outside of this chaos, which Roland tells me today was called behavioral formations, is basically just the interaction between these agents to agents. So they have no concept of the overall form. The actual form work itself just comes purely out of the emergence of the interaction between these behaviors. But we had to take it a little bit step further. So like Roland develops these things over the course of about 15 years. And about 7 or 8 years ago, he was creating these incredibly intricate and complex geometries, and recognized that he was getting sick and tired of creating them purely digitally. He wanted to make them into the real world. So that began a long and fairly rigorous exploration into how exactly he could accomplish that. And this entered into a sort of feedback loop where what he eventually realized was, in order to accomplish the real-world maintenance of these things, you have to take into considerations of the material properties of what you guys are going to be working with. So in this case, The project for the Central Pompidou was made using SLM printing, which is a powder-based printing. We did it out of aluminium, so this was a piece of metal. And the assumption was that printing with SLM, which is powder-based printing, there wouldn't be a huge amount of constraints with that. Mainly, you wouldn't have to worry about draft angles or cantilevers or anything like that. Turns out we were fairly wrong about that assumption. You're only allowed to have a 30-meter drift from horizontal, and you can't have a span of more than about maybe 3 or 4 millimeters. The reason being that if you're breaking out those rules, you tend to wind up with drag that happens across the bed. So that's when the next bit of powder comes down onto it, the swiper that comes down, breaks off little pieces, they drag across the powder, and all of a sudden your print starts delineating based on that. So, as you guys can see, we're talking about something here that has roughly a million different agents. So the geometry is fairly heavily complex. To go through there and to try and tidy up something like that, to make sure that every single rule, or like every single element adheres to those rules, would be quite arduous. So these were behaviors that we had to then, after we come up with this generated form, had to then loop back in and build in the behaviors that would, one, create enough structural integrity within this thing, but also allow it to be printable. So basically this was roughly around the time where I sort of interjected myself into practice there. A lot of the stuff I'm talking about I've inherited from about several generations of people that have come through Roland's practice. And a lot of them were ex-students who have gone on to do some pretty phenomenal things. Fingers crossed. So anyway, this is just a small animation that's kind of highlighting, I guess, the overall formwork of the project that went into the Pompidou. Unfortunately, I don't have any photos of the finished one here, but if you guys Google it, it's probably a pretty impressive little thing. So sorry, these are just like a couple of illustrations of the various behaviors here. So we have the normal cohesion, separation, alignment kind of ones here. We deal with ones that are based on like attraction to curves or attraction to mesh fields, or where we actually use the vectors of meshes as individual agents that have their own logical behaviors. And so the way that the practice actually works is that a lot of the time we will diagram these things up. We will translate these into vector-based forces, which is like what a lot of physics-based programs tend to work with. We write out the pseudocode, and then like before we used to run with Java, we now operate with C# because it allows for a better interface within Grasshopper. And we have a very talented guy within the lab at the moment that is trying to get multi-agent systems to work with AI-based systems. So he started doing the hard thing of parsing all the Java code that Roland wrote over the years in C# so that we can actually interface with Grasshopper. And we love him for it. So as I guess a little bit of a third branch of what Roland's practice works with is teaching. So we use the classroom as, I guess, a kind of breeding ground where we give over a lot of the code or a lot of the processes that we've started to develop to the students, and we try to see, I guess, what outside influences can actually come up with that. If there are tricks that we are missing, or if there are just interesting ways that we can actually explore these things that you are like basically just brute forcing the amount of things that we can sort of examine our options here. What we're looking at here is a result from a suite of studios that Roland ran, and now he used to run this with a character called Mark Gibson, who was a very talented designer that came through his studios, and now I've kind of taken over his role a little bit. We're calling this, well, Roland calls this painterly objects. So what we mean by that is that when you run algorithmic-based functions onto something to generate form, it's very hard to lose the indexicality of that. And what we mean is that it's always very obvious when something is produced digitally, because oftentimes the systems are fairly obvious. Like you can see a huge amount of authorship over the top of that. So what we do is, predominantly through programs like ZBrush, we go in there and we do manual alterations on these things, and sort of softening and combining processes in order to kind of eliminate the indexicality of it through, again, what we call painterly sort of processes. So the idea of coming in there and applying a sort of intuitive logic onto these ones, into something that is largely mathematical and physics-based. And so I guess the pursuit of these objects was basically just, one, the pursuit of the novel, so stuff that has been unseen. And a conversation that we tend to have within these studios is always around the notion of strange, in a similar spirit to that. So what we insist that the students don't do is that they don't undermine or overmine their work, and by that we mean that they don't try to reference their objects back into any kind of context. So they can't justify these things by saying, I was inspired by water, so I tried to make something that looked like it was flowing or draping like a curtain or something like that. And they can't overmine it by basically saying, well, I just ran it through the process and it can spat this out, so therefore it must be good. They have to look at their objects as though they are subjective things to be taken isolated and be critical of that. So extracting what characters they can out within it. And so they start building up these sort of suites of strange generated forms that, we get them to pump in about 20 of these every single week, so they get really, really good and really, really fast at it. At the moment in the studio, we're getting the kids, we recently started looking into ceramic 3D printing. So what we have at the moment with the students is that they are generating these forms with the idea that they will use it to create some sort of prototypical formwork, so like a staircase or a roof or a ceiling, and you can't, probably looking at this, you can't really see how these could possibly be architectural elements within it. These are basically early explorations to just kind of like loosen up the students to kind of like generate elements that they can go in there and sort of mine for inspiration, and also to sort of challenge the ACT of what these elements could be. So what is the virtue by which a staircase is a staircase? And how can you challenge what that is in a very sort of formal sense? We're also obsessed with color, and we are very, very critical of some of the colorings of these. So that kind of like brings me to, I guess, the point where I was mainly interjected into this studio, which is when Roland started looking seriously at polymer 3D printing. Again, this largely came about around the time when Roland's was about several years into figuring out ways that he could take these complex ideas of his and try to bring them into reality. And up until this point, it had been more that similar to the sort of the early Computational experiments we term as agent bodies, and the basic reason behind that is because every single one of those planes has a complex skeletal rig on it, which then has limbs which leak out, form a sort of complex surface-like lattice, and so hence the term agent bodies. Roland started off mainly by generating the agent bodies and then figuring out some sort of skin work to be cast over the top of that. 3D printing kind of inverted that system, where he started to consider the idea of, well, what if you manufactured the skin that these things would be cast, manufactured the skin, and then had the complex structural systems cast inside that one. And so there's several, well, there's three things that we try to combine into these processes here. One, which is obviously structural consideration. Two is trying to combine that and trying to make that into the formal detail of the whatever we're actually trying to create. And the third one is manufacturing considerations. So trying to combine all of these, like these three balls that we're trying to juggle here, into an outcome that satisfies all three of them, basically. So this was a project that Roland proposed for the NGV, and you guys can see that it has a very similar kind of like agent body structural network that is running through it. And the proposition was that we would 3D print this and then cast this with concrete into these conduits. The gold was going to be gold paint so that you guys wouldn't read the materiality of that one. And here's a couple of experiments with this. This was done in polycarbonate, which we eventually had to stop using because we were told we might burn down RMIT. flash point of it was like way lower than the temperature that we actually had to print with, so we're working around it. So yeah, this is just a little bit of technical detail. You guys can get the basic gist of the idea of how this thing would work. This was a relatively simple version of the earlier idea, though. So, and the reason why that was because we were limited by toolpath. So basically, when you're printing, the toolpath refers to the path that obviously the bead actually has to take. And they found that you got the best results by having a singular continuous toolpath, one that didn't stop, start. And this was like obviously in the very early stages of this, so it's something that we've been moving along and trying to really develop. But the formal complexity of it is obviously very limited by that fact. So this is like part of a prototype that was actually starting to be made. Unfortunately, it never panned out. They proposed it for another little artistic installment that never saw the light of day, unfortunately. So what did see the light of day? This was the flow exhibition that was done for Melbourne's Triennale, that was done at the NGV. This was done under extremely short time frames. We had 2 months to design, manufacture, and install this thing into the NGV. It hurt. It comprised of 70 individual 3D printed polymer panels onto it. All of that is complex planar CNC timber milled elements that our workshop guys basically slaved over for us, thankfully. And then a complex network of steel structure that goes through, which is also built on the agent body design algorithms. This was done in collaboration with a sound artist called Philip, sorry, I'm going to mispronounce his name for a second. Sorry, Philip Samatsis. I practiced that so much. And the mouse is... I think I paused it. Just help.
It's Control L.
Yes.
What's his name again?
Philip Samatsis, that's him there. And he's a soundscape artist, so he basically went to the... Okay, so it's just going to stop there. He went to the Antarctic and recorded sounds of the ice shelves cracking, and then brought them back and sort of amplified them throughout the Great Hall. You guys can see that there was a general theme that came out of that one. Now, we obviously don't like to undermine our own work by saying that, you know, we decided to make this thing kind of start looking like an iceberg, but I'm going to leave it there for a second. That wasn't the general intention, but that's what the NTV kind of wanted. So we tried to make this this atmospheric piece. They actually asked us to put a fog machine into the ground, which we were very skeptical about, but that didn't turn out horrible. So the relationship between the steelwork and the polymer in this project was a bit of a nightmare, because what we wanted to do was we wanted to interlace, we wanted to try and get as close to this original concept that Roland had been pushing at this point in time, where there would be an integration and a synthesis between structure, formal outcome, and manufacturing sensibility. And this project, just given the shortage of time, is not obviously the greatest realization of any of these things. This thing was, as far as we know, it still is the largest 3D printed polymer object in the world. But it doesn't strike, it's a far cry from, I guess, the early experiments that you guys saw as digital experiments. So the skin was generated during a surface expansion algorithm where every single vertices was basically treated like mesh, well, was treated like an agent. So they all adopt their own basic behaviors, which is that they want to expand surface of the mesh topology. They don't want to get too far away from each other, but they also want to maintain a certain degree of angle between their edge conditions towards each other. So it's a bit like a matrix algorithm. Okay, so we've just got a video of the panels being made. Each of these panels took about maybe 4 to 5 hours to print out, which is relatively quick considering their complexity. Just stopping halfway through each video. Sorry. So again, every single panel was individual, but obviously not extremely individual. We didn't have the opportunity or the luxury of time to really push the premise of this one. This was the steel structure, so the polymer is already laced between each of these ones. And then we wrap it together. We had what we really ideally would have wanted to have done would have had a polymer structure that went through this one. The engineer told us no, and rightly so, because there wasn't any data that we could use that would inform his calculations. We worked with an engineer called Boman, who is fantastic. He's probably one of the only few people that we know that can actually calculate and work with the stuff that we give. And he did the calculation for the steel in a day and a half with me sitting next to him, just kind of like fussing. Like, he wanted to put members in one place, and I said it couldn't go there, Roland would not allow it, and he would just glare at me. And make his point very well known, but he would carry on, and yeah, he's very, very good. And then, so we translated that steel into the thicknesses and dimensions. We had an unroll script, which I guess isn't all that exceptional these days, sent it off to the fabricators. And every single one of these steel members, there was 367 of them. They were all individual, all different forms. So in order to put them together, hopefully I got some photos of this. This is the workshop guys working on the timber facing of this, which in itself wasn't an easy feat. So 70 panels, 367 steel members, 3 days to assemble it. So we used VR. Because we couldn't give any of the guys that were assembling this actual architectural drawings for them to follow, just because of the complexity of this object and how long it would take to actually read that. It was mostly someone sitting down with a laptop trying to work out where all these things go, and then the guys with VR headsets on them trying to just once we had the members assembled, they would just work out where they would go into place, and it turned out to be a fairly efficient system. It was the first time that we didn't have warm-up days or anything like that where we tried the system out or anything like that. We basically gave them the VR headsets and said, go. They were an exceptional crew. I don't know when this video is going to cut out, but we'll see how they go.
It was working fine.
Yeah. So, as a little bit of plug, the VR technology is called hologram.
AR.
Sorry, AR. They call it VR. Go onto the hologram website.
Is it? No, it's augmented. It's not virtual.
Have it out with them then.
I will.
They're off in Talon at the moment.
Doing the timber.
Doing the timber thing. They just finished it off.
Right, so the hologram guys are also RMIT grads.
No.
RMIT grads. They teach at RMIT.
So you got a great grad.
Teachers at RMIT.
So yeah, this is just a 3-day time lapse, and you guys will see patrons come in, and then 2 hours later we were allowed to move the barricade because the paint had dried. That's how down to the wire this thing came. So that was flow. Sorry, yeah, that was flow. We then had a commission for a piece that wasn't ever realized. It's still kind of in a holding pattern. It might happen. but it was for this oceanarium in Portugal, and this one started to get towards the closest realization that Roland had up until the project that we're working on at the moment. A couple of reasons why this thing had kind of like jumped into the next level. We made some pretty huge advances with the 3D printing scripts that we tended to work with. They were much more robust and they could handle things like stop-start a lot better, non-linear printing, which is basically the idea of like non-horizontal based printing, so your layers can actually move up, and that obviously requires a huge amount of calibration just because you're dealing with it's a nightmare, bead thicknesses, temperature changes, large amounts of fluctuations over the top of it. So basically we had to come up with a 3D printing script that was fairly intelligent, but what is, I guess, is really lacking at the moment is real-time feedback systems where we can actually gauge what the outcomes of these things are in real time so the robot can respond to that. So that's the next thing. So it was a huge project. It was going to be about 350 square meters, well, about 10 tons of printed polymer material. It was absolutely monstrous. Hopefully it will still be absolutely monstrous. We'll see how it goes. But what we entered into when we came into this one was, again, this is talking about that feedback loop where we design, I guess, algorithms that come up with the formal character that we want to go with. And then we have to go backwards and try and work out the means that we're going to use to manufacture this and try and adapt those algorithms based on the limitations that we're going to have. So as a bit of a quick example, draft angle limitations. This was an early kind of like chunk piece of this thing where we just ran it through and then we did an analysis. So everything you're seeing in red is not going to print. And to put this in, I guess, a little bit more context, I was the only guy working on this project. That piece there is 6 meters high off the ground. It's big. And that's a lot of cleanup. Yeah, so basically an impossible kind of like challenge for one person to prepare and then deliver, because we do a lot of our own manufacturing to deliver this kind of project. So what we try to do is we try to obviously optimize our process as much as possible so that most of the manual challenges are excluded out and we can automate and make repeatable as much as possible. When things fail, I don't think that's a great photo, but when things fail, they fail pretty badly, and it has catalytic effects here. So like every single bit of red mark on there, even if we had like one red mark, that bit fails. It's not going to just be like a glaring hole. The entire thing is a domino effect where the rest of the thing will just absolutely cark it on you as well. So gravity is the worst. This is the rationalized version of this one. This is what it's going to most like. This is what the first assembly is going to look like. And we are halfway through production of this one at the moment. We've got about another 4 weeks to get this thing onto a boat over to Shenzhen, so I'm not sleeping all that much. But they're starting to come out. I've got a photo hopefully of someone standing behind it. They're fairly large elements. They take about 22 hours to print. So by no means are they simple. But yeah, things are coming along with that one. Anyway, thank you very much.
Anyone got any questions?
Why do they have to be composite? Is it because the only thing you can print with is not structural?
Yeah, so ideally what you would want to, like, the problem with most polymers is that they aren't great in compression, and specifically they're not great in point compression. So the problem is that you have any part of it that's taking more pressure than the other part if it's not evenly distributed, you're going to get cracks and fracture lines that fall through it. They can take a fair amount of self-weight, but certainly, like this thing is going to weigh probably about 500 kilograms. There's not really a plastic out there that can take that much self-load. And the other problem that we have is that we're printing on a print bed that is only 700 by 1400 millimeters wide. So we can't print this thing in a single piece at the moment. Everything's going to be part of, like, you can see that they're all individual parts that are going to have to be joined together, and which means that there's going to be a lot of opportunity for there to be point loads on this thing, which, you know, it's just not going to handle it. it's also cantilevering out about 3 meters above people's heads, so there's a huge amount of pressure onto those joints.
On that topic, real quick, how do you join them together? Is it
A very, like, it's, at the moment it's steel. It's a steel connection that we're prototyping and trying to get working. We're not entirely sure if that's the most rational method that we could be doing so far. Like, the obvious, like, thing that we would have liked to have done would have figured out, like, to figure out a way to thread carbon fiber through the entirety of this thing and cast it in situ. But because this thing has to come back to, like, this is going to the Shenzhen Biennale and then it's coming back to Australia. So we've got to be able to disassemble it. Otherwise, we would have gone with that method.
well,
Oh, okay. So obviously the stuff that you guys do now, which is extremely amazing, seems to be somewhat limited in scale. Have you thought about what that means translating into bigger scales and sort of larger built, almost building-like forms? Because obviously then the problems scale as well as the size of this thing.
Yeah. So as far as we know, this stuff could be applied to the side of a large-scale building. Like we see polymer probably working better with tower-type topologies than having more like interior kind of like elements rather than, I guess, more domestic-scaled things. You're right, it does become a little bit more of a problem, but that comes down more, I guess, to the structural elements that you try to feed into this. You basically want to just figure out a method that takes as much of the stress and load off the formwork and carry that over as much as you possibly can into the structure. And then there would have to probably be a primary structural system that you feed that back onto. So I don't see you ever, I guess to answer your question, I don't see you ever being able to take this in its current form and making a building purely out of this. This is probably more in the realms of cladding at this point in time. I wouldn't see this replacing actual floor members for a variety of reasons. It's not very thermally impressive. You would have to fill it up with something that has better properties than that. I don't know exactly how you would ever get like something like this purely watertight, which is a whole like extra host of issues in that one. But certainly, like, yeah, we think it's at the point where it could be a very scalable object. The only other problem is just like commercializing it. Right? You've got to basically teach someone how to do everything that you're doing, and then you have to train them up every single time a new project comes in. Because what we find, every new project that we enter into has a unique kind of like aspect to manufacturing that we have to redesign. So we would be perpetually teaching whoever is making it for us how to make it for us.
So might lead on from that, but what's Roland's ultimate goal? What is he? Is there something he's aspiring to? Like he's really ultimately trying to achieve?
I think he would love to see a tower built out of this stuff, but certainly like just I don't think we've ever fully had the conversation about like, you know, what's his magnum opus ever going to be. So I feel like at this point I probably would be speaking for him, but we've definitely spoken about, you know, tower typologies being appropriate for this formwork. We've definitely spoken about like more domestic scaled stuff with some of the, so within the research lab we're looking at, we recently just got a CMT welder that we're going to attach to the end of the robot so that we can do large scale 3D metal printing. We're trying to upscale ceramic printing to the point where we could use it for domestic scale products. So ceramic we think has more potential to be a domestic scaled object. So if you are going to build a house or something out of that, like ceramic makes a lot more sense. So yeah, I think he doesn't really have an end goal of something that he's shooting for.
Yeah.
Every single project is just about trying to basically accomplish the things that he started 15 years ago, but also do it on a tiny, little bit larger scale each time round, which is basically what all this stuff has been. It's just like one stepping stone to the next stepping stone to the next one. And we'll just see, I guess, eventually where that stops. Yep.
Is all the production currently done through RMIT, or do you outsource some of the printing?
We're in conversations about outsourcing it to other people, but because of a whole bunch of paperwork, I can't actually mention anybody. But that is a conversation that's been happening for a while now, for a lot of different areas. We have a lot of grants that we're using to develop that. But yeah, currently it's a bunch of very, very tired usses sitting down watching this thing print. The robot room doesn't have windows, so
I'm just curious whether you guys have, on the side applied this concept to, let's say, urban scale in terms of the city, how that will form.
Roland has, definitely. I wasn't involved in that project. That was way before my time. He's certainly not the first urbanist that's looked into emergent styles of, environment. I don't know if agent algorithms is particularly appropriate for that kind of stuff. I think that was Roland's eventual decision. Like, he was doing it fairly. Where was he doing that? I think he was doing that at Columbia, he said, or something like that, but I could be completely wrong. We talked about this ages and ages ago, so sorry, I can't give a proper answer about that, but certainly, like, it was looked into, and I think he kind of abandoned it.
Anyone else? Awesome. Thanks, Charlie.